This is a force example problem of finding a force to hold up a picture. Here's the problem we're going to be looking at. It says, my husband is trying to decide how to hang a picture, so he makes me hold it up on the wall for him. I press the 0.5 kilogram picture up against the wall with a force angled at 30 degrees from vertical, and the coefficient of static friction between the picture and the wall is 0.65. What minimum force can I apply to the picture in this way and still keep the picture from sliding down? Let's begin by thinking about what kinds of forces are acting and how it looks. Here's my wall, and here's a picture. I'm going to be applying a force using my hand, and it's at an angle of 30 degrees from the vertical. If I'm pressing the picture against the wall, then the wall presses back, which means there's some normal force. I know that the picture has some weight, which points down. And finally, the problem specifically mentions a coefficient of static friction. Static friction, or kinetic friction, always acts parallel to the surfaces in contact. And so I know that in this visualization, the friction force needs to point straight up or straight down. Static friction will point whichever way it needs to point in order to keep the object from moving. The problem talks about a minimum force, which means just barely enough force to hold it up. So if there were less force, it would move down. This tells me that the force of static friction is pointing up. So let's get going on this problem with the picture. Here's the picture. Free body diagram. It has weight pointing down. It has a static friction force pointing up. In my diagram, it has a normal force pointing off to the right, and then up and to the left is a pushing force. If I add an XY coordinate system to this, here's the X is horizontal, Y is vertical, and the problem tells me that there's a 30-degree angle between the pushing force and the positive Y axis. So some of the things that I know about these forces, I know that the force of static friction needs to be as big as it can possibly be to help hold the picture up. This will minimize that pushing force. And so I'm going to set it equal to the maximum value of static friction, which will be mu sub s times the normal force. I do have a number for mu sub s, and so the force of static friction is going to be equal to 0.65 times the normal force. At this point, I'm not sure exactly what the normal force is. This is kind of an unusual situation where normal force points in a horizontal direction, but I do know something about weight. Weight is going to be equal to the mass times the gravitational acceleration, and so that means equal to 0.5 kilograms times 9.8, that's meters per second squared. And so the weight in this problem turns out to be a 4.9 newtons. Finally, there is something that I know about the force of the push. I can break that down into x coordinates and y coordinates. So in the x direction, my total force pushing in the x direction is going to be whatever the overall force is times the sine of 30 degrees. And so let's take a quick look. Here my force of pushing is off at an angle. There's 30 degrees between the force and the direction of the positive y-axis. And so my x component is going to lie here. This is the opposite side of the triangle with the 30-degree angle. This is where the 30-degree angle is. And then my y component is going to be the cosine. So if I get back over here to my side work, the force of the push in the y direction is going to be the overall force times the cosine of 30 degrees. Alright, let's make a table. So I'll write down every force, its x component, and its y component. So the first force that I'm going to look at is this force of static friction. It does not act at all in the x direction. It does act in the y direction, and it's positive, 0.65 times whatever the normal force is. As far as that normal force goes, I know that it acts in the positive x direction and not at all in the y. The weight does not act in the x direction, but acts in the y direction, and it's a negative 4.9 newtons. And then finally, this force of the push, which is going to equal, in the x direction, we have the overall force of the push times the sine of 30 degrees. The sine of 30 degrees is 0.5. So this is the overall force of the push times 0.5 for the sine of 30 degrees. And that is a negative x direction. In the y direction, it's acting positively, and it's the overall force of the push times the cosine of 30 degrees, which as a decimal with 3 sig figs works out to 0.866. Alright, that is the complete table, and I've run out of room on this page, and so I'm going to go to another page to add up the components and set them equal to mass times acceleration. Alright, I've gone ahead and added up and written out the sum of the forces in the x direction and the sum of the forces in the y direction. Now, it's probably a good idea to just double check what the question was asking us to find. The question was specifically asking us to find this force of the push. What is this force of the push required to keep the picture in place? And keep in mind we are taking advantage of static friction to its maximum extent to minimize this pushing force. Well, I have two equations, and in each case there's some stuff I don't know. There's a normal force and there's a force of the push in each case. So what I'm going to do is I'm going to use one of the equations to isolate the force of the push, and then I can substitute things into the second equation, and that should give me something that I can algebraically solve. So just to start at the top, because that makes more sense to me, the sum of the forces, according to Newton's second law, has to equal the mass of the object times its acceleration in that same direction. And so this all has to be equal to the mass of the picture times its x direction acceleration. The picture is stationary, and so that means that the acceleration is 0, and so the sum of the forces has to be 0. So 0 is equal to the normal force minus the pushing force times 0.5. I can add the pushing force times 0.5 to each side, and that will give me 0.5 times the force of the push is equal to the normal force. Alright, so here's the game plan. I am going to take what I know about the normal force and substitute it into this second equation. Since the picture is entirely stationary, in the second equation the sum of the forces is also equal to 0. And now this is going to be 0.65. That normal force was equal to 0.5 times the force of the push. This all got substituted in for that normal force. And I still have the force of the push times 0.866, and then subtract off 4.9 newtons. So I'm going to take a simplification step, and the 0.65 times 0.5 is 0.325 times the force of the push plus 0.866 times the force of the push minus 4.9 newtons. All that should be equal to 0. So if I combine the terms with the force of the push in it, if I add 0.325 to 0.866, then I will get 1.191 times the force of the push minus 4.9 newtons, has to be 0. I'm going to add the 4.9 to both sides and then divide both sides by 1.191. So 4.9 newtons divided by 1.191 has to equal the force of the push. So the force of the push winds up being equal to 4.1 newtons. And that has solved this problem.